Okay, so we have a related rates of change question, and this is a question about the volume of a cube, a sugar cube, shrinking over time or decreasing over time. We're actually told in the question that the cube is put into coffee, and when it's put into coffee, it decreases at a constant rate. So that means that every second that passes, the volume of this cube decreases by the same amount. And how much is that? Well, it decreases by 1 over 20 centimeter cubed per second. Now, we're going to write down in notation what that is. So that's the change in the volume of the cube. So the change in the volume is dV as time passes, dt. So the volume of the cube is changing. It's decreasing, so we're going to put in a minus 1 over 20 centimeters cubed per second. So that's the first thing. We'll always be given some information, concrete information, a number in the question about how something is changing. Like, so the volume is changing or a radius is changing, something like that. So that's the piece of information we're given. The next thing we're going to do is we're going to look for the question. The question is, what's the rate of change of x of t? Now, x is the side length. So they're asking, what's the rate of change of the side length? Like, so if we draw it in here, this is x. We know that the volume of this cube is decreasing. It's decreasing by minus 1 over 20 centimeters cubed per second. The side length is obviously also decreasing, but it's not decreasing by the same amount, and it's not decreasing in a linear way. So what we're looking for is the rate of change of the side, dx, as time passes. Okay, so it's important now to use our chain rule to change dx dt into dx over something multiplied by something over dt. So we have the dx on the top and the dt on the bottom. We need to place something here and here. It has to be the same thing so that we can do this question by joining two other formulas together. This question would be really easy if we had a formula which had x's and t's. So if I said the side length x is t squared plus 2t, then I could easily find dx dt. We just use the power rule, 2t plus 2. But I'm not given a formula with x's and t's. I was given information as to what dv dt was, and I was asked to find dx dt. So we can see that the other letter in this question is clearly dv. So I'm going to put dv here, and I'm going to put dv here. Now, we already know dv dt. dv dt is minus 1 over 20. So that's here. What we need to find is dx dv. So to find dx dv, we need an equation with v's and x's. V is clearly volume. We have a cube up here. The volume of a cube is going to be x by x by x, which is x cubed. And so if we have the volume as x cubed, we can find the rate of change of the volume with respect to its side, dv dx, which is 3x squared. Now if we have a look, we're not looking for dv dx, we're looking for dx dv. So we're going to have to turn this upside down. dv dx is 3x squared, but dx dv is equal to 1 over 3x squared. So I'm going to sub this in for dx dv. So we have that the rate of change of the side with relation to time, dx dt, which is what we're looking for, is dx dv, which is 1 over 3x squared, multiplied by dv dt, which is minus 1 over 20. Now, if I tidy that up, I have minus 1 over 60x squared. So not a very satisfying answer from the point of view of this isn't a number, it has an x in it, and that's because the rate of change of the side depends on what the side length is at a particular time. We're interested in the rate of change of the side when the cube is 1 over 64 centimeters cubed. Now the question is, what is the side length that would give a volume of 1 over 64 centimeters cubed? We need to find that side length because that's the particular instant that we want this rate of change. So it's pretty easy to do. We know that the volume is equal to 1 over 64, and the question is, what's the side length at that time? Well, x cubed is the volume, so x cubed is equal to 1 over 64. And if we get the cubed root of 1 over 64, we get that when the volume is 1 over 64, the side length is 1 over 4, or 0.25. So we're going to sub this in because that's the instant. When x is equal to a quarter, that's when we're interested in what's the rate of change of that side x. So the x dt is equal to minus 1 over 60 by a quarter squared, which is equal to minus 4 over 15 centimeters per second. So when the cube has a volume of 1 over 64, the side length is 1 over 4, and the rate of change of the side length is minus 4 over 15 centimeters per second. So just to summarize it again, maybe a little neater, the volume of a cube is equal to x cubed. We need to make a formula for the rate of change of x with respect to t. We can do that by breaking dx dt up into dx dv times dv dt. We've been given dv dt in the question, so dv dt is the rate of decrease of the volume of the cube with respect to time, which is minus 1 over 20. We can find dx dv by differentiating the formula for the volume of this cube. So dv dx is equal to 3x squared. We're looking for dx dv, so we're going to turn that upside down. We get 1 over 3x squared. And then we put that all together, and we have dx dt is equal to 1 over 3x squared times minus 1 over 20, which is equal to minus 1 over 60x squared. Now, we're looking for the rate of change of the side with respect to time at that moment when the volume of the cube reaches 1 over 64. So if we let the formula for the volume of a cube, x cubed, equal 1 over 64, we see that the side length would be 1 over 4. We're going to sub that back into dx dt, and we can find that the rate of change at the instant when the cube is 1 over 64 is minus 4 over 15 centimeters per second.